Astronomers studying the Kuiper Belt have detected in its structure a subtle but statistically significant warp, one that current models of the solar system cannot fully explain. After analyzing the orbits of more than 150 distant objects, researchers found that the outer region does not align the way it should. Simulations suggest the distortion may be caused by an unseen planetary mass object informally called Planet Y, smaller and closer than the proposed Planet 9. In this video, we will break down what was discovered, how strong the evidence is, and what it could mean. Let's get started. The discovery did not begin with a new image, but with a structural analysis of motion. Researchers focused on how the average orbital plane of Kuiper Belt objects behaves as distance from the Sun increases. Between roughly 50 and 80 astronomical units, EU, the belt's mean plane aligns closely with the gravitational influence of the known planets. That alignment is expected, especially given Neptune's dominant role in shaping nearby trans-Neptunian objects. Beyond about 80 astronomical units and extending toward 200 astronomical units, however, the data revealed a deviation. The average orbital plane appears tilted relative to the inner solar system. In other words, the Kuiper Belt seems warped. The deviation is not visually dramatic, but it is statistically meaningful. After correcting for observational bias, a necessary step because surveys of distant objects are not uniformly distributed across the sky, researchers tested whether known planetary masses could account for the distortion. Simulations incorporating the current solar system configuration could not reproduce the observed warp. When an additional planetary mass object was introduced into the models, the distortion aligned with the data. The simulations indicate that a body with a mass somewhere between Mercury and Earth orbiting approximately 100 to 200 astronomical units from the Sun could generate the observed gravitational influence. This hypothetical object has been labeled Planet Y. It has not been directly observed. Instead, its presence is inferred from the collective behavior of distant objects. The method is grounded in gravitational dynamics. When motion does not match prediction, additional mass may be required. Historically, this approach has precedent. Neptune was discovered after irregularities in Uranus's orbit pointed to an unseen planet. The difference here is scale and difficulty. Objects at these distances are faint, slow-moving, and challenging to detect. The current finding is therefore a dynamical signal, not yet a confirmed planetary discovery. The researchers emphasize that the warp detection is statistically strong but not definitive. It suggests that existing models may be incomplete. Confirmation requires more data. One of the first clarifications made by researchers is that Planet Y is not the same as Planet 9. Planet 9, proposed over the past decade, is theorized to be a distant super-Earth, possibly 5 to 10 times Earth's mass, orbiting several hundred astronomical units from the Sun. That hypothesis was developed to explain clustering patterns in the orbits of extreme trans-Neptunian objects. Planet Y differs in both scale and purpose. It would be smaller, closer, and proposed to explain a warp in the overall mean plane of the Kuiper Belt, rather than orbital clustering among a small subset of distant bodies. This distinction matters because it suggests that the outer solar system may not be shaped by a single dominant unseen object. Instead, its structure could reflect layered gravitational influences. If Planet Y exists, several formation scenarios are plausible. One possibility is that it represents a leftover planetary embryo from the early solar system. During the era of planet formation, numerous protoplanetary bodies formed and interacted gravitationally. Many merged into larger planets or were ejected from the system. Some may have survived in distant stable orbits. Another scenario involves planetary migration. Models suggest that the giant planet shifted positions early in solar system history, scattering smaller bodies outward. A Mercury to Earth-sized object could have been displaced during this process and settled into a distant orbit. A third explanation is that current surveys underestimate the number of mid-sized objects in the outer solar system. At distances of 100 to 200 astronomical units, even relatively large bodies reflect little sunlight and moves slowly across the sky, making detection difficult. The reported statistical confidence of the warp is high, meaning the signal is unlikely to be random. However, statistical strength depends on sample size and survey completeness. As more objects are discovered, the robustness of the warp will become clearer. What makes this study notable is its population-level approach. Rather than focusing on isolated anomalies, it analyzes the collective geometry of a large region. That broader analysis reduces the likelihood that the signal is produced by a few unusual objects. If confirmed, Planet Y would require revisions to current dynamical models of the outer solar system. It would indicate that the planetary inventory is not yet fully mapped even in our own system. The next phase of investigation depends on expanded observational coverage. The Very Rubin Observatory's Legacy Survey of Space and Time, LSSD, is expected to significantly increase the number of known Kuiper Belt objects. Over a 10-year period, the survey will repeatedly scan large portions of the sky with high sensitivity, enabling the detection of faint, slow-moving bodies at great distances. A larger data set will either reinforce or weaken the warp signal. If the distortion persists as more objects are added, the case for an additional planetary mass object strengthens. If the signal diminishes, the hypothesis may need revision. There is also the possibility of direct detection. A Mercury to Earth mass object at 100 to 200 astronomical units would be faint and difficult to observe. Its detectability depends on its size, reflectivity, and current orbital position. Sustained monitoring and motion tracking over time would likely be required. Even if direct imaging remains challenging, confirming the warp would still carry substantial implications. It would suggest that current gravitational models of the outer solar system are incomplete and that additional mass influences orbital structure. More broadly, the study highlights how much remains unknown about the distant regions of our solar system. While thousands of exoplanets have been identified around other stars, the outskirts of our own system remain partially unexplored. It also reinforces the importance of dynamical methods in astronomy. Planetary discovery does not always begin with a visual observation. Subtle deviations in orbital motion can reveal unseen influences long before direct detection becomes possible. Over the coming decade, improved surveys, refined orbital calculations, and independent analyses will test the Planet Y hypothesis. Scientific progress depends on replication and verification. A single compelling signal invites further scrutiny. Consistent confirmation establishes discovery. If Planet Y is confirmed, it would represent one of the most significant additions to our solar system's map in modern times. If ruled out, the process will still refine our understanding of Kuiper Belt dynamics and planetary modeling. Either outcome advances planetary science. A measurable warp in the Kuiper Belt points to the possible presence of an unseen planetary mass object. The evidence comes from orbital dynamics, not direct observation, and remains under investigation. In the coming years, new surveys will determine whether Planet Y is real or simply a gravitational puzzle. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.